So this is an outline. So we will continue with Shor's factoring algorithm. We have started that last week, and I want to finish it. And there's only one other item on the menu for today, and that's another computational model. That's adiabatic quantum computation. So I thought it would be good if we have a bit of variation in the computational models that we see here so that you get an idea of what is possible. There's different ways in which you could think of using quantum mechanics for computation. And about these details we'll speak later. Let me just quickly say, first, yeah, there's an idea involved, like there was for the circuit model. It came out of classical reversible computation. So there is an idea here why you would want to use quantum mechanics in that way. Yeah, and there is a footnote or a catch. We'll get to that. And we'll talk about the equivalence between the circuit model and the adiabatic model, where it holds and where it does not. Let's begin with Shor's algorithm, or let's continue with Shor's algorithm rather. So maybe I'm going over a few slides that I already showed so that we get back into thinking about it. So Shor's factoring algorithm does something in cryptography. Namely, it's anti-cryptography, so to speak. It breaks the RSA encryption. Yeah? So RSA is what you use when you go shopping with a credit card, and the quantum computer can break that. So when quantum computers, useful quantum computers become available, maybe you have to switch your credit card for something else. Yeah, okay, good. Yeah, let's put this a little bit into perspective. So here you see an array of cryptography schemes. So let's first put RSA in place, the thing that a quantum computer attacks. So there's two axes here in this diagram. So there's the axis of security. So high security means unconditional. It's not conditioned on any assumption. Lower security, still sometimes of interest, is security given certain assumptions hold. So you make these assumptions and hope that they hold. And often these assumptions relate to the hardness of computational problems. So you believe that a problem is hard, maybe you cannot prove it, but you think it's hard, and then the security of the scheme relies on this problem being hard. And this is exactly what RSA is about, and we'll see. So this is a weaker form of security. So then there's another axis in this plot, and this is practicality. If a cryptography scheme works in real life. So an example for low practicality but high security, unconditional security is the one-time pad. Yeah, you share a random bit string with your, with the person you communicate with, and then it's very easy to communicate securely. You just take a piece of that random bit string, add your message to it. On the other end, the receiver subtracts the bit string again and gets the clear message. And for anybody else, all CFD encoded message for anybody else is just random bits. Can't do anything about it. Okay, so that's unconditionally secure, but the problem is you have to have met with the person you want to communicate with. That's kind of one reference point, yeah. Unconditionally secure, impractical, and the other reference point is conditional security only, but practical. So they are both compromises. This is where you want to be, unconditional security, practical. Yeah, so quantum cryptography sort of lives in this box, so you can have that. So since we can do better than that, even with classical technologies, we don't need to think about that. So we want to talk a little bit more about RSA, about that box here. A practical, but only conditionally secure. So this is what will be attacked by a quantum computer. So we know that this computational assumption that provides for the security of RSA breaks in the presence of a quantum computer. Let's talk a little bit about that protocol before we talk about Shor's algorithm. So here comes the computational assumption of RSA. So this is all about an integer, a large integer number that is promised to be the product of two primes. And if you have the primes, then it's easy to multiply them to get that number, but the inverse problem is believed to be hard. It's not known, but it's believed to be hard. So if you have this number, getting the factors out is a hard computational problem. I mean, if this number is 15, then maybe you can do it in your head, but if it has 15 digits, then it's already significantly harder, and if it has, I don't know, 1024 digits, then it's getting kind of hard. Yeah, so this is a hard computational problem, although it's believed. There's no proof of that. So we know, so the best classical algorithm, the best algorithm that solved this problem has this complexity. So it's almost exponential in the number of digits of the of this number n. Yeah? So the complexity measure is the number of digits that it has, how much paper you need to write it down. So it is not exponential precisely in that length of that number, but exponential in that length to the power 1/3. So overall, the cost is less than exponential, but much higher than polynomial. In a quantum computer, the cost is polynomial in the number of digits, much less than this. And I think it's polynomial of degree 2, I believe, 2 or 3. Yeah? So fairly doable from a scaling perspective. Okay, and that is why the quantum computer can break RSA, and we want to talk about how that works. But before that, let's talk about the RSA protocol itself. So let's see how this protocol uses the hardness of getting the factors back from this number for encrypting messages. Okay, so our setting is that we have a sender A and a receiver B, and A wants to send a message to B. Okay, so the protocol starts with the receiver. So it's somehow indicated to the receiver that a sender A wants to send a message. So the receiver picks two large primes and multiplies them and broadcasts the product to the whole world. There's nothing secret about it. Everybody can know that product. So now the sender uses this product n to encrypt a message. So there is a message and there is an encryption map, and that's now computationally efficient, that gets the encrypted message out of the clear message, and that encrypted message is also broadcast. Again, potentially to the entire world. Nobody can be excluded from receiving it, and the protocol doesn't require it. Okay, so now the receiver, among many others, receives that encoded message and uses the two prime factors that make n to decrypt the message. So the encryption works with the product, the decryption works with the two factors separately. Okay, so that's the protocol. So let's review what's public and what's private and what an attack to this protocol could be. So public is this product of primes and the encoded message. Private is the clear message and these factors. So since everybody knows the encoded message and this product, if it were computationally viable to get the prime factors out of this product, then everybody who could do that could obtain the clear message from the encrypted message. Okay, so, but that's precisely the assumption that the protocol relies on. Nobody can do that. Nobody can get the prime factors from the product. But a quantum computer can, and this is how a quantum computer attacks this protocol RSA. Let's talk about how this protocol proceeds. So this is now Shor's algorithm in an outline. Yeah, so this is how it attacks RSA. Okay, so there is 4 steps. Let me see. Is there another? Yeah, there's a 4th step. Okay, so most of this is classical. There's only one quantum piece sandwiched in between classical parts of the algorithm. So, yeah. So maybe I begin with that. So in Shor's algorithm, the original problem of finding these prime factors in the composite is reduced to period finding. So we will see how this proceeds. This computational problem is all about n. So n must appear somewhere in this formula. So this mapping a to some integer exponentiated with a modulo n, this is a periodic function, and the goal will be to find the period of that function. Okay, so let's see how a quantum computer can help with that, but before we see how it can help with that, let's see how this is embedded into classical stuff. Okay, so here it begins. So n is what we want to factor, and we start with a random integer n. Now, pick a sufficiently large integer or any integer and compute the greatest common divisor of it with n. So if this is not 1, then we are done. Yeah, if this is not 1, we obtain one of our factors. So that's rather unlikely. So most likely we will continue. We have to continue. And so if the greatest common divisor is 1, so that these two have no common factors, then we continue with the rest of the procedure. So, okay, so next step, and this is the step that we will do quantum mechanically. So we use a quantum computer to find the period of this function. So what this function does, it takes the random integer that we have chosen, exponentiates it with the argument, and then looks at this whole expression modulo n. So it's modular. This is happening in modular arithmetic, not with respect to the integers. I mean, not with respect to all integers, but only integers mod n. Okay, so that would be classically hard. I mean, we could do this classically, but that would be hard. And we will do this quantum mechanically. But we come to that, how we do that later. Okay, so next thing is once we have the period, which is of course a function of m, we check if this period is even or odd. So if the period is odd, that was bad luck, and then we have to start over, and it's about 50-50. Yeah? So yeah. So now suppose after a while we were lucky and we find an even period. So then for the period holds the following thing. So let's look at these expressions. We have 2 factors here. If p is even, then we can form p over 2. So we have m to the power p over 2 minus 1 times the same plus 1. So we can multiply that out, binomial formula. No, nothing very complicated here. This is m to the power p minus 1. And this is 0 mod n. So m to the power p is just 1 mod n. So this is just the expression for p is the period of this function. Okay. Good. So, so this is just kind of how we can formulate our assertion that p is the period of the function. And so now that we have that, we check whether this thing or that thing is a multiple of n. Yeah? If that happens, that's again bad luck. But if it does not happen, we continue. And that is still sufficiently likely. So there is bounds on the success probability of progressing to step 4, which comes next, and I think it's about 1/4. So you're losing not too much in these checks here. Yeah. Good. And so so now that we found that neither this thing or that thing is a multiple of n, we compute the greatest common divisor of either of the factors with n. And that is supposed to give us one of these factors. So let's briefly recap why this is so. So what matters now is the factors, the prime factors in n, p and q. So what we have just excluded in the third step of the protocol is that both prime factors go into the same factor over here. Because if they did, that thing would be a multiple of our integer n. So this means now one of them, say p, ends up here, and the other one of them ends up in here as a factor. So and that's why when we compute the greatest common divisor, we get these factors p and q out. Okay, so that is the algorithm. And so what remains is to explain this second step here. So why, how do we do this? Classically, this is not an easy thing to do. Okay, so that is the quantum thing that I would like to explain. We have to talk about step 2, the period finding. So that we haven't explained yet how to do. Okay, so now it's going to be quantum. And so what we do is we use 2 quantum registers, and their size has something to do with the length of the bit string. So n is our number, logarithm base 2, integer part thereof, this is our length L. I mean, the length of the number in binary digits. And so we have one quantum register, is the first. It has twice as many qubits as this length is. And then we have another quantum register that has exactly as many qubits as this length is. Okay, so that's what we are using. Okay, and so here is now how the quantum algorithm begins. So in the first register that has this length, we prepare an equal weighted superposition of all computational basis states. So I don't know, maybe the term computational basis states, computational basis has occurred before in this lecture, but I am not sure I explained it. So the computational basis is the eigenbasis of sigma z. Yeah? Spin up, spin down, also called 0 and 1, that's the computational basis. And so now we are dealing with a tensor product of such states. Yeah? 2 L qubits over here in this first register. Yeah? So this is a number A that goes from 0 to 2 to the 2L minus 1. So that makes a superposition of 2 to the 2L components. Yeah, everything same amplitude. Yeah, and this is the normalization factor. So this is how we prepare the first register. Second register, every qubit is prepared in the state 0. Now comes the first step. Now comes the modular exponentiation. So remember, this function of a, m to the power a mod n, so that was the function whose period we cared about. Yeah? And so what we do now is we take the state that we had, which had superposition of all a's in the first register, and 0 here into that superposition. And so what is the register that does that? So the transformation is transformation. Let's see how I write that. Okay. Transformation. Okay, so what I didn't say is how we actually did that. Yeah? How we actually got from there. So we have to, the least thing we have to show is that there is a unitary transformation that does this for us. Huh? And then we also have to show that this is computationally efficient. But yeah, modular exponentiation is a classically efficient circuit, and we can just build on that. So I don't want to go to this level of detail, but at least I want to show that this transformation is unitary. And so what we are doing is we apply the transformation how do I write this? So this is the sum over all let's write it as A over all A. It's not good in notation, so it's not good. So let's write it like this. B goes from 0 to 2 to the 2L minus 1 tensor X. So this is a spin flip of Okay. Basically what's happened is conditional spin flips, like the C naught that we had. So X stands for a Pauli operator, but it's now not a Pauli operator on a single Q, but it is a tensor product of Pauli operators potentially, and whether you have a Pauli spin flip X in a particular location, yes or no, that's decided by this bit string. Just to give an example for what I mean with this notation, just X, say, of 0, 0, 1, 1 would be identity on particle 1, identity on particle 2, X on particle 3, X on particle 4. Yeah? Something like this. So that's the gate that you do to get from here to there. And so maybe it's good for you to convince yourself of that. And the other thing is you want to show that this is unitary. Why is this unitary? What you'll find is that this gate is squares to the identity. That's the first thing you will find. And that has to do with the fact that a Pauli operator, no matter what it is, so this can be will be a bunch of X's here. Oh, by the way, these are tensor products. I hope this was clear. So Pauli operators square to the identity. So that's the first thing, no matter what they are. Okay, so that is the first that you will realize. So you will end up, when you square it, with the sum over all projectors, and that's just the resolution of the identity. So that's the first thing. Second thing you'll notice is that this thing is self-adjoint. Yeah? So you find that in total you find that T squared is the identity, and T is also T dagger, so you find T dagger, and T dagger T are both the identity, and that's the condition for unitarity. Yeah? And so if we think, if it is unitary, then we can make it in principle, that is universality, and then we also have to show that we can do it efficiently, this transformation, and we do this by harvesting the classical circuit for that, modular exponentiation. Next thing, second step is that we measure the second register Okay? So we are so far in this state, and well, all values between 1 and n, or 0 and n minus 1 occur in this register, and now we measure it. And since this register at that stage was entangled with that register, you know what entanglement does, so there will be an effect on the former register as well. Yeah? And we cannot choose what the measurement outcome on that register is going to be. We have to live with what we get. All right, so this register is projected, and that register is projected too, but not into a single value, but rather multiple ones. And namely, we retain all values in here such that they satisfy this condition. If you take our initial integer m to that power a modulo n, then you get the measurement outcome s. All those values a that satisfy this condition, they remain in the superposition, and everything else is gone. Yeah, so that is the effect of that projection here on the second register. Okay, and so now this set of a's that satisfies this condition has a structure. And that's because we have a periodic function here. Okay? And because this is so, we can write that down here. So there is a smallest value of a appearing in the superposition, and then all the other values that occur, they are larger by a multiple of the period. Yeah? So the amplitudes here, they form a periodic function. That's kind of a peak, then nothing for a long time, another peak, nothing for a long time, another peak, and a bunch of peaks. Yeah. Okay, so it's a periodic function. And that is what we want to get something out of. Any idea how that can be used? Yes, red sweater.
The Fourier decomposition.
Oh, you already, yes. Why? Why Fourier decomposition?
Because we do have a periodic function.
That's true. But the function, yes. I believe you mean to say that if I have a periodic function, the Fourier transform is also periodic, and I want to use this. But why don't I use the periodic function that I have here?
Well, I don't remember, but I assume, well, the function is periodic. Okay?
Yeah.
If we do the Fourier transform, we don't get a periodic function. Right?
No, we don't. I think we do. Oh, no, wait. Oh, I apologize. You are right. We have a periodic function of delta peaks. Kind of a lattice, something like a lattice, and that makes a difference. I mean, yeah. Yes, I mean, sorry, thank you for that comment. The sine function is, for example, a periodic function, and the Fourier transform of the sine function is not a periodic function. It's just a peak here and a peak over there. Okay, so sorry, we have a bunch of delta peaks periodically spaced apart. And when we take that thing, then the Fourier transform is a periodic function as well. And we will be using periodicity, that's true. So all who have heard about Shor's algorithm before, so why are we not using the periodicity of this function? Okay, good. Then let me say it. Let's not. Oh, yes. Mm-hmm.
Maybe you want to
The offset. The offset is exactly the problem. So it turns out we will have to measure multiple times. So we will not get by with a single measurement. And so let's try this here. Now we have measured that register. We measure the first register now. We get a peak located somewhere. Next time we get to the stage of doing that, measure the second register, we will get, in all likelihood, a different value. I mean, we will have to wait very, very long before we get the same value again, because there are so many. So next time we have a different offset. And so we cannot relate these two peaks at all. Yeah. So we will not see a periodic pattern. We'll just see random signals, and that's because the offset's going to be different every time. Yeah. So that's why the periodicity of the function here doesn't help us very much. And now what's going to happen though, if we do the Fourier transform, then the offset, the horizontal offset, will translate into what? Yes? Into a phase. Good. Let's talk about that. So that's step 3. We do this Fourier transform. This is what the formula is. So let me just fix this. This is K. Yeah. So every basis state goes into a superposition of basis states with a bunch of phases in front. Yeah. Okay, good. And there's also an efficient circuit for doing that. I don't have it here in the slides. It's in the lecture notes if you want to have a look. And now we are exactly doing as you said. So after the Fourier transform, we measure the first register. And so the offsets, they translate into phase factors that we don't, I mean, they go away under measurement. Yeah. So so the probabilities for obtaining an outcome corresponding to this peak or that peak, they don't depend on those phase factors. Yeah? When I go from amplitudes to probabilities, these phase factors, they drop out. And so I have converted something that was harmful, namely the horizontal offset, into something that's harmless, namely the phase. Okay, but the period has also changed. So the period P that was now relates to the period that we now have in this reciprocal fashion. Yeah. And you also see that there is some, yeah, so that's the relation. So this is the period that we'll measure. This is the period that we care about. They are related in this fashion. So I measure this, hopefully sufficiently accurately, and then compute P from that relation. So, but you immediately see that there is some degree of approximation involved here because P has no reason to divide that power of 2 up here. Yeah? So, yeah, and so another way to say this is the function that we are talking about, I mean, this periodic function, m to the power p, not an integer number of periods will fit into our register, but a very large number of periods and then a tiny little bit. And this tiny little bit spoils the periodicity, and therefore what we really be measuring is a distribution, a kind of narrow but nonetheless distribution of values, and therefore also the value for the period P that we infer will carry an error. And all of this would have to be taken into account carefully, but not at the level we are discussing it here. So by and large, we measure this period and infer that period. Okay, so now in each run, I mean, I was assuming that we measure that directly, but that's not the case. So what we will be measuring is a peak location of the Fourier transformed function. And so we'll do this a couple of times. So each time we get a multiple of the period. So we compute continued greatest common divisors, and in this way find the period. Yeah. Okay, so that's the end of it. Shor's algorithm is a main motivation for quantum computation. So, I mean, okay, kind of shopping with other people's credit card is maybe not so nice, but it tells you that quantum computers have power. They can do something. And yeah, so that's why, yeah, it's not the only motivation for the field, but it carries quite a bit of weight, Shor's algorithm. Good, and so that's why it is in this course. It has nothing to do with computational models, except that we got a little bit of practice with a circuit model, but it is the motivation for doing any further analysis, yeah, that you have these examples for algorithms. Good. So that is the end of the first part of this lecture. So the next part, the second part, is the adiabatic theorem. So this is a different computational model, completely or fairly different intuition goes into it. And that's the reason I review it here. Something that we want to follow very much in this lecture, but at least we want to mention it so that you get to see a spectrum of things. Okay, so so first let's talk about the overall idea. So there's actually maybe two ideas that go into this. So the first idea is, hey, what about, we are physicists, yeah? So we like Hamiltonians, and so why not encode a problem and its solution into a Hamiltonian? Seems a natural thing to do for a physicist, but we have to actually do it. We have to find a way of doing that. Okay, so we construct a Hamiltonian, we call it HF for a reason that will become clear later, of a bunch of qubits. So qubits are our workhorse here, and it has two properties. First, that it is diagonal in the computational basis. So remember, computational basis was the eigenbasis of the sigma z's. So, well, what's important here about the computational basis is only that it is local. And so the readout is easy to handle physics-wise. Okay, so we've just specialized to the computational basis because I need only one. And so I use this, but it's a local basis, so it's easy to measure in. That's the reason for requiring it. And the other requirement is that the ground state should contain the answer to a question that I encode in the Hamiltonian. So I encode the question into the Hamiltonian, and from the ground state I get the answer. So that's the idea. And now the question arises, what kind of questions and how is this implemented at all? Yeah, so here's how. So consider a bunch or a set of Boolean functions. So they take bit strings into individual bits. So n bits of input, 1 bit of output, Boolean function. A number of them. And now we set up a system of equations. So for every one of these functions, we say that this function applied to some n-bit bit string is supposed to evaluate to 0. The Boolean function evaluates to 0 or 1, and we require that for bit string x, it evaluates to 0. And that is supposed to hold not only for this function, but for a number of them. So I have a system of nonlinear, in general, binary equations. Yeah? That's these equations here, and I want to know which x, if there's such a thing, satisfies them. We want to have a solution x0 to all of these equations. So that's my problem. That is what I want. Okay, and so now here is the Hamiltonian of which the solution of the system of equations, if there is such a thing, is the ground state. Yeah? Okay, so we have a double sum here. So first, this is only numbers. Hamiltonian has unit of energy, so that's why we are putting the constant here in front. But other than that, it's a double sum. And one of those sums is over all states in a basis of our Hilbert space. So this is our computational basis states. And the other sum is over these equation labels up here. So we are checking every constraint. So this is basically we are going through our Hilbert space, or a specific orthonormal basis of it, and for every state we are checking which, or how many rather, conditions are violated. So the energy that is going to be assigned to each of these basis states is J times the number of conditions that are violated. Yeah? So the more conditions I violate, the higher up in energy. And if there is a solution, that solution will have energy 0 because solution, no conditions violated, and this will be the lowest possible energy state. All the others violate at least one condition, so they will be higher. So that's the Hamiltonian that we want. So that was promised. Yeah? So a computational problem is encoded into it, and the ground state is the solution. And furthermore, by measuring in the computational basis, that is the eigenbasis of sigma z's, I can find out, assuming I somehow manage to get the system into the ground state of this Hamiltonian. If I can do that, then I can even figure out by a simple measurement what that solution is. So that's the idea. Okay, so all that remains to discuss is how the ground state of such a Hamiltonian can be reached. Okay, so how do we reach a ground state of something? We cool. Okay, yes, that's something we can do. But sometimes this doesn't work. Yeah? So sometimes systems like glasses, for example, they have difficulty finding their ground state. And it takes them a very long time to get reasonably close to the ground state. So, and I guess everybody who has ventured into numerical optimization in high-dimensional spaces especially knows these landscapes with local minima to get stuck in. Yeah, so finding the ground state may not always work. We will run up into a similar difficulty, but so the fathers of adiabatic quantum computation, they knew that, and so they proposed another avenue for preparing the ground state of such a Hamiltonian. What is this? What they suggested was to use adiabatic evolution. Okay, so what is this? So you pick a Hamiltonian that you know the ground state is easy to prepare. So that could be, for example, the Hamiltonian given by a local magnetic field. Yeah, so it would look like this. So all the spins are pointing in the positive or negative x direction, depending on whether B is positive or negative. Okay, so each spin is individually pointing. So that's easy to prepare. Yeah, so that's what you start with. And then you apply a continuously varying Hamiltonian. So the Hamiltonian is a function of time, and it is made of two parts. So the first part is HI, the simple Hamiltonian with the simple ground state up here, And the second part is the other Hamiltonian that we have discussed so far, the one that contains in its ground state the answer to a computational problem. Okay, so you see that the contribution of this first Hamiltonian, it diminishes over time. So it starts strong, and then as time progresses from 0 to our final time, capital T, it continuously goes towards 0. So this is also what it gets its label from. This is EI is for initial. This is the initial Hamiltonian. And so here it's the other way around. So this term starts with no weight at all, and then it is continuously ramped up. So it will have full weight at the end of the evolution. That's why it is called HF. F stands for final. This is the final Hamiltonian, and you interpolate between the two continuously. Okay, and so now, such a thing, if T is large enough so that the Hamiltonian changes slowly, is called adiabatic evolution. And so it so happens that if you are in the ground state of such a Hamiltonian to begin with, you stay in the ground state of the Hamiltonian throughout the evolution. So in particular, at the end, you are in the ground state of that Hamiltonian, which is what we wanted. We wanted to be in the ground state of that Hamiltonian, and this is a way of doing it. Okay, so and then the final step is to measure in the computational basis and extract what is hopefully the solution. So that's the overall scheme. Yeah, so we are using adiabatic evolution to solve a computational problem. Just one comment here. So what guarantees the working of this is called the adiabatic theorem, and we'll talk about the adiabatic theorem a little later. So it says that if you're moving slowly, you are staying in the instantaneous ground state. Of course, that state may change because the Hamiltonian changes, but you always stay in the ground state. I want to look at an example of this. And that's the example I've chosen here to look at that because it's reasonably simple, is but interesting. It's simple but interesting. This is the maximum independent set problem. So this is a problem that has to do with graphs. So graphs are things that have vertices and edges. So every graph G has a set of vertices, the dots, and it has a set of edges. These are the links between the dots. Yeah, and so now, maybe I better draw this. So now a maximum independent set is a subset of the set of vertices. Okay, so let's just kind of look at one or two examples. So this is our graph. Oh, this is not a particularly interesting example. No. Let's look at this graph. So we have 4 vertices, 4 edges. Okay, so let's see. Okay, we pick this vertex. Is this vertex an independent set? Yeah, there is no edges between vertices of that set. Okay, let's continue. Is this an independent set? I say, yeah, super. 2 heads shaking, nobody nodding. That's a good turnout. Yeah, so this is not an independent set because there's an edge between. They are not independent. So no, this not. But this here, these two, they form an independent set. Yeah, because they have no edge running between. Good, and that's also the largest independent set. I can try to add any other vertex, and well, I will always fail the independent set condition. So this is the maximum independent set for this graph. Oh, well, it's one of them. Huh? So we also have the other. So we have 2 maximum independent sets here in this case. Good. Okay, I hope this clarifies the concept of maximum independent set. And we can now ask ourselves the question, so given a graph, how complicated is it to find a maximum independent set? And so this, and this is what makes this problem interesting. So this question is NP hard. So let's talk about complexity classes for a bit. Yeah? I said earlier that quantum computation is about the efficiency of computation, and this is what governed by complexity classes. Quantum computation is not about what is computable. And everything I can compute on a quantum computer, I can also compute on a classical computer, but maybe much more slowly. So it's all about the complexity of computation. So maybe it's good to talk about complexity classes once. Okay, so there is this class NP. That's what we want to talk about. NP. That's NP. I'll say in a moment what it is, and it has a subset that's called P. And let's begin with explaining that. So P is the problems that a computer can solve in polynomial time. NP is the class of problems that a computer can verify in polynomial time. P stands for polynomial, NP stands for non-deterministic polynomial. Don't ask me why it's called like that, but it means that not necessarily I can find a solution to the problem at hand in polytime, but at least I can verify in polytime if a solution is given to me. So that's another thing. It's not the same. And and so P is contained in NP. Whether the two are distinct is actually an open problem. I mean, everybody believes that, but there exists no formal proof of that. Okay, so we have to talk about what NP hard is, and maybe also what NP complete is. So let's begin with NP hard. So this is NP hard. So, and now our problem here, MIS is somewhere here. So, so NP hard means at least as hard as anything in NP, or as hard as anything in NP. So this means that anything in NP, you have a problem in NP, you can map it with in poly time, you can map it to the maximum independent set problem. Yeah? So if you had a solver, why am I telling you all these many things? If you had a solver for maximum independent set, then you could, if that was efficient, then you could solve all of this huge complexity class NP. Yeah, and that would be a tremendous thing. So that is why this seemingly artificial problem of maximum independent set is of relevance. Because, well, if you could solve that efficiently, you could solve this entire class NP and probably more. So maximum independent set is probably not in NP, but this is not required for NP hard. Yeah, it's just that anything in NP can be mapped to it efficiently. So the NP hard problems that are also in NP, they are called NP complete. And that's the last term that I explain, NP complete. So this is NP hard plus in NP. Okay, Good. And so there's a decision version of independent set, and that goes like this. So does this graph have an independent set of k? That's the decision version of the problem. And it's easy to see that this is an NP, because suppose you have a solution. So you have this supposedly independent set. Well, you can check very easily the independent set condition. Yeah. Where was it? So this condition up here is easy to check. And it's also easy to check whether it has size k. You just count the vertices in that set. So it's not very hard. Okay, so the decision version of independent set is NP complete. And the optimization version of the problem, that is maximum independent set, is NP hard. So if you have given the set that is supposedly maximal, how do you show that? Yeah, so it's not obvious how you test that in polynomial time. Good. Okay, but bottom line, maximum independent set is a very hard computational problem, and so if we had a quantum algorithm solving that, that would be an incredibly powerful tool. So that's sounds almost too good to be true. And we have to figure out where the catch is, if there is one. But before we get to that, MIS is even nicer than that. So something that we have so far totally glossed over is how hard it would be to make that Hamiltonian. Yeah, I mean in physical devices. I mean, we want to get by with few body interactions. And so the question is, can we make this Hamiltonian with few body interactions? And it turns out we can make this Hamiltonian with basically the simplest interaction there is, namely with the Ising interaction. Two body, very special kind. Okay, so we are just writing down this Hamiltonian again. So, yeah. So here is, so X is our bits. So bit string, this is an index function for the set. So if component xi of this bit string, or bit I, is 0, this means corresponding vertex is not in the set. And if xi is 1, then it is in the set. Okay, so now you check if xi and xj are both 1, then they get an energy penalty if I comma j is an edge. So this is the this relates to the independence condition. Yeah, so we don't. Yeah, so we don't want this to occur. So if they are both 1 and this is an edge, then it's not an independent set. And so this is penalized with a certain amount of energy. Okay, and then so that's what we want to enforce very, very rigorously. And so we want to maybe give a huge energy penalty to that, because we don't want to consider such strings anymore that violate this condition. So here it's a little bit different. Okay, so what this term does is, it counts the number of elements in the allegedly independent set, and the larger that number is, the more an energy reduction you have. So you get rewarded if that set is large. Now you get a penalty when you're violating independence, and you get a reward when your set is large. So what you will end up with, hopefully, is something that a configuration, the lowest energy, you should have for the independent set of maximum size. You just need to be careful, a little bit careful with choosing the constants here, or rather the ratio of the constants, because this you want to enforce very strictly. You do not want a single of these conditions violated. Yeah? So So this is the dominant condition, and so you need to make sure that this J here is sufficiently large compared to that B. So maybe you can figure out what the critical ratio is. I don't go here to that level of detail. Okay, but the important thing about this is that this is two-body interaction. This is just one particle interaction with an external field. So this is feasible. Okay, so we see right here that this is only, I mean, a local Hamiltonian, the kind of one and two body interactions. So that's feasible. But let's kind of, let's look at it and, I mean, let's belabor this point a little bit more and switch from binary variables, 0, 1, to spin variables, plus, minus 1. So this is more natural for the physicist. Okay? So you can easily check that Zi equals minus 1 maps to Xi equals 0, and Zi equals 1 maps to Xi equals 1. Okay, so we have replaced these binary numbers by spins up and down. And if we just plug this expression for Xi in here, then we are getting that. So the degree of the polynomial is not changed, but now we have it in spin up and spin down. Okay, so that's what you get, and you can write it in a little bit of a simpler fashion. So these are just Pauli matrices, and you recognize the Ising interaction right here. Zi, Zj, or for you physicists, sigma Zi, sigma Zj. Okay, we leave the sigmas out. Okay, Ising interaction plus magnetic field. Okay, so it doesn't get any simpler than this. Okay, so MIS has two nice properties. So first, it is NP hard, hence interesting. If you have a solution for that, that would be a very good thing. And also, it's easy to implement because all you need is an Ising Hamiltonian plus magnetic field. Yeah, this is not, I mean, so this is what the company D-Wave does if you're following D-Wave, or has done for a very long time. So I'm not saying it's easy, but it's feasible. And D-Wave has taken this a very long way. Good. Okay. And it's also, if you look at these things, looks almost too good to be true. Yeah. It's so you begin to wonder if there is a catch. So what is so outstanding about this is that it's strikingly powerful. You allegedly solve a problem, problems of this kind, and also it's a one-size-fits-all solution. You don't have to think about algorithms. You just switch on your Ising couplings, and that's it. Yeah. Okay. Now the catch. So there is indeed a catch, and that is what we want to talk about now. We begin filling in this diagram up here. So what we have here on here. So what we have here on the vertical axis is an energy scale, and on the horizontal axis we have time. So we begin with time 0 and end with time t. And so what's plotted here on the vertical axis are the eigenvalues of the various energy eigenstates we have. So yeah, a bunch of eigenstates, and their eigenenergy vary over time. And so in particular we have the ground state. We have the ground. Okay. In particular, we have the ground state, and yeah. So the problem that occurs is here. So it will. I mean, phenomenologically, it turns out that in all or many cases, most cases, there will be a point in the evolution where where the ground state in energy comes very close to the first excited state. And that is a difficult spot to be in. In a place like this, it is hard to maintain the adiabaticity condition. Okay, so let us revisit the adiabatic theorem. Let's talk about the adiabatic theorem. So, and the adiabatic theorem exists in countless versions. This is an early version, not the best version, but it's good enough for us. We are asking, okay, we have to run slowly through this. How slow is slow enough? And that is answered by the adiabatic theorem. So it talks about the total duration of the evolution, and it relates it to various points of various quantities of interest for this problem. So delta is this energy gap here. So this is delta. Yeah. So the difference between the energy of the ground state and the first excited state at the point where it is the smallest. That's what we call the energy gap. And then we have another parameter, gamma here. It's defined over here, that has to do with how fast the Hamiltonian changes. Yeah? So this is a rescaled parameter, actual time divided by the duration. Yeah, and we're taking the derivative of the Hamiltonian with respect to this parameter, square it, and then take the operator norm of that. Okay, so this gives us an idea of how drastically the Hamiltonian changes over time. Okay, and so now the runtime is larger than that ratio. So what matters for us is that the smaller the gap, the larger the runtime. Yeah? And so it turns out, I mean, it's phenomenologically it is the case most of the time. In certain instances, and generally that's hard, but in certain instances you can prove it. But the dominant behavior that we see is that the energy gap is exponentially small in the system size. So n here is the length of our bit string, yeah? So the bit string whose solution we want to read off. Okay, and so if this gap is exponentially small in that, the runtime becomes exponentially large in that. And so here goes your quantum advantage. That is the Achilles heel of this computational scheme. Yeah. There is one final thing that I'd like to discuss about the adiabatic model, and that is the equivalence of it to the circuit model. Yeah. So there's a theorem. It is here from that reference. I mean, I will not go into too much detail here. I just want to advertise their construction. It's a quite ingenious construction. Yeah, but anyway, these people here have proven that the adiabatic model is polynomially equivalent to the circuit model. That is, I can simulate, say, the adiabatic model through the circuit model with polynomial overhead, or I can also simulate the circuit model with polynomial overhead by the adiabatic model. So either can efficiently simulate the other. That's what it means to be polynomially equivalent. Okay, so and so we'll go through that a little bit. One remark here, so just a reminder that the adiabatic model requires zero temperature because we are in the ground state, and we can be that only if we are not coupled to a bath with finite temperature. Okay, so and that's of course an idealized situation. So later we will have to talk about a little bit what changes when you remove this this constraint and ask yourself, so what's going to happen when the temperature is small but finite? Okay, but I'm getting ahead of myself. So for the moment, we assume this precondition of zero temperature, but this is, of course, an idealization. Good. Okay, so, well, here's the theorem. The proof has two directions. The first direction is the circuit model can simulate the adiabatic model in polynomial time. And the other direction is the reverse, namely that the adiabatic model can simulate the circuit model in polynomial time. So I will talk here only about the second step because that's the kind of ingenious argument. The first direction, yeah, I mean, remember what the adiabatic computation was. It was unitary evolution according to Hamiltonian that varied in time. And circuit model does unitary evolution, so you just trotterize together that evolution with the Hamiltonian changing in time. Okay, so conceptually, this is not very hard. You have to take care of a bunch of epsilons and deltas, and that give you the computational cost. But conceptually, it's straightforward. So the fun direction is the second one, namely that the adiabatic model can simulate the circuit model in poly time. And I mean, all details are in the paper down here for which the reference is given. I just want to mention it a little bit. So, so what you do, the way you do it is that you construct a Hamiltonian. So in adiabatic quantum computation, we always have to think about how to construct this final Hamiltonian. Yeah, okay. And so, yeah, and so what this final Hamiltonian is, what its ground state looks like, the way it simulates the circuit model, it doesn't have in its ground state the final state of the quantum register in the circuit model. Instead, so what it gives you is a history state. That's the superposition of the circuit model quantum register at all times. Oh yeah, but then there's another thing. So this is not the only thing that exists. So this register is entangled with another register, and that's a clock register. So this is basically time ticking that tells you, what the time is at which you have the state of the quantum register over here. Okay, so that's the clock. Maybe there's a little bit of detail, maybe too much detail, but the valid clock states, let me say it like this. Maybe the first thing that you would do is encode the time in binary notation. That would seem perfectly reasonable. They do it differently. They encode the time in a unary fashion. So that is way less efficient, but not critically inefficient. So, I mean, if L is your maximum time, if you do it in binary, then you need log L bits, log L base 2 bits. Now you need L. That seems unnecessarily large, but you gain in another way. So to make the adder for binary notation is a comparatively complicated beast. To make the adder in unary notation is much, much simpler. And that advantage of having the much simpler clock ticking forward operation, that weighs out the disadvantage. So that's why the unary encoding of the clock. So at time L, you have L ones followed by the remainder of zeros. Okay, so that's what it is. And so now you have the equal weighted superposition of clock at time L and state of the quantum register at time L. Yeah, and that's summed over all times. So that is what the Hamiltonian will prepare for you. Yeah, and then you will measure this Hamiltonian. Yeah, you will measure the clock register, and you want to find final time, but that will not always happen. Yeah, so there's a certain inefficiency associated with that, but that's all fine with polynomial overhead. Yeah, and if that works out, then you measure the quantum register. Yeah, so this is how you can read out the quantum register from this. Okay, good. So all I want to do is to explain a little bit what this final Hamiltonian looks like. I mean, only a little bit. So there is an initialization Hamiltonian. So that piece is there for making sure that the initial state alpha of 0 is, I don't know, all qubits in 0 or something like that. And also the clock is supposed to be initialized in 0. So this is all in the initialization part. And so then there's the clock Hamiltonian. And the clock Hamiltonian enforces this unary encoding. Yeah, so for example, a register value 1010, that would not be compatible with unary encoding. And so there must be an energy penalty for that. And that's what the clock Hamiltonian does. So it gives everything an energy penalty that is not a proper encoding of this proper unary encoding of time. Okay, that's what this is for. But now the interesting part is that. So this is really the part of the Hamiltonian that makes for this superposition here. And this looks as follows. Yeah, so this is two parts. So what you see here, I mean, this is part of the clock register. So what you see here is the clock ticking forward from here to there. You go from L-1 to L in time. So that's what's happening here. And correspondingly, you have the unitary, the Lth gate in the circuit here. Okay, so this is a projector tensor with a unitary. So that is Hermitian. This is typically not Hermitian. And so you have the Hermitian conjugate down here to match that. So both together are Hermitian. So this term makes you go forward in time and apply the unitary to the first register. This term makes you go a step backward in time and apply the inverse of the unitary. So yeah, okay, good. And so that this Hamiltonian piece enforces this relation between various branches of the superposition, which is exactly what you want to have. So you can show that. So the history state that we wrote is indeed an eigenstate of that Hamiltonian, and it is in fact the eigenstate with the lowest energy eigenvalue. So the ground state is also something that we wanted, and you wanna know about the gap, and the gap is 1 over the length cubed. So it's a polynomial in the length, and in the time duration. And so, yeah, so the Adiabatic theorem tells you that you pay a price when you do this adiabatic evolution towards this Hamiltonian H final, but it remains polynomial. Good. Okay, so this is basically the extent to which I wanted to explain that construction. And all details you find in the paper, if you want. So, so let me summarize. So what these people established is that adiabatic quantum computation and the circuit model of quantum computation, they are polynomially equivalent. Either can simulate the other with polynomial overhead. And here we are talking about the perfect models. So this is at temperature 0, this is with no errors at all. So nothing like real world. And so we wonder, what about imperfections? Okay, so imperfections, so these are gates with errors, and thanks to the threshold theorem of fault-tolerant quantum computation, if the errors are small enough, they don't change the computational power at all. So even if this is erroneous, it can do exactly the same as the perfect circuit model does, and that can, of course, simulate adiabatic quantum computation. So if error occurs here, the model doesn't break down, at least not immediately. There's a point when it breaks down eventually. Okay, over here it's different. So for adiabatic quantum computation, nobody has yet invented any powerful stabilization mechanisms that would be comparable to the threshold theorem over there. So when the temperature begins to deviate from zero, which is of course a realistic situation, there's no software techniques as of now, maybe there are some, have not been invented yet, that can restore effectively the t equals 0 condition. Yeah? So you lose computational power in this model. So at finite temperature, it is unclear whether the finite temperature thing can simulate the circuit model, and it is expected that it cannot. But there's no proof of that at the moment. Yeah, okay. So this, brings us back to a broader scenario. So the adiabatic model is a computational model. We will look at other computational models, measurement-based quantum computation with magic states. And so something that we will often do is, okay, model A, model B, how are they related? Are they polynomially equivalent? And all the models that we talk about in this course are polynomially equivalent. So next thing that you will ask is, well, what about noise? What about imperfections? Does the computational power of these models go down, or can it be maintained for reasonably weak perturbations? Yeah, so you do this in other models. So does the model remain equivalent to itself under noisy conditions? And for all, for all the models that we will discuss from now on, all these equivalences will hold. So they will all be polynomially equivalent, and they maintain their power under sufficiently weak noise. So diagrams like that, poly equivalences, is something that we will come back to.